let's continue. So here's what we covered before the break. So if we have some region, omega, so this region is, and let's say we have one curve. This is curve gamma, and we have another curve. Let's call it alpha. So the question that we try to investigate is, what are the conditions for the integral of a holomorphic map over gamma to equal the integral over of the same holomorphic map over alpha? Holomorphic in omega. Okay? So the condition is that if there is a homotopy that goes inside of the region omega, if I can gradually deform gamma into alpha, the two integrals will end up being equal. And the proof of that was really hurried, so I'm sorry about it. But it's in Stein, and it's written there pretty well. Okay? So this leads to considerations of basically, so generally when you have homotopy, you want this region to have no holes. If it has no holes, then more homotopies are possible, right? Because one possible problem that you can have here is that there is a hole and then you cannot go around that hole. And that hole represents some singularity of the holomorphic map. That's where it's not differentiable. So for that, what you say is, as a definition, that omega is simply connected if any two pairs of curves curves gamma and alpha with same endpoints are homotopic. Okay? So basic examples of simply connected regions. I'm sure you already have much better examples. So any disk D. So if you take any disk, and if you take two curves that have the same endpoint, here is gamma, and here is alpha. Then what is the homotopy between gamma and alpha? Yeah, so what you can do is you can just pull the points by invisible strings. So you just take this point, by t takes this point and pull it together. So straight line homotopy. So we can say that the homotopy would be f of st equal to t times gamma of s plus 1 minus t alpha of s. And so basically the disk is convex. Disk is convex, so you can just do this type of manipulation. So that's the easy example. So also not too hard to show is that the slit plane. Which is C minus let's say maybe write like this, minus infinity to 0. Kind of that's a little because there's only one infinity, I suppose. You get it, right? So the slit plane is simply connected. And the reason for that is, here's the slit plane. So I can view the slit plane like this. Or, I mean, I can look at the polar representation of all those points. If you look at the polar representation, this is what? So the angle theta is between let's say minus pi and pi, right? And the radius is bigger than 0. So really, from the polar perspective, I can look at it as here is the radius, and this is minus pi, this is pi. So I can view this region like this, and this is in this region I can with any curve drawn in this region I can just have a simple homotopy there. So the way you just say that is if gamma is equal to, let's say, gamma of s. I can write it in polar form as r of s e to the I p of s, and I can write alpha of s similarly as, let's call it r sub gamma, and this will be r sub alpha of s e to the I theta of s. And then I can create a homotopy as follows. I can create the functions r st to be simply t times r of gamma of s plus 1 minus t r sub alpha of s, and I can create the angle theta st to be equal to, let's call it maybe this would be phi sub gamma, this is phi sub alpha. So that would be t phi sub gamma of s plus 1 minus t phi sub alpha of s. Right? So those are the homotopies that are corresponding to the curves in this region. So all you have to do now is then f of st. It's just going to be r st e to the theta st will be the homotopy between those two curves. Make sense? So the curves are. So you just translate to what is the angle component and what is the radius component, and use a homotopy. So more intuitive definition of something simply connected is that the object is connected and the complement is connected. So you can have a general statement would be every region inscribed by a toy contour is simply connected. So just a very silly question, maybe. So we have this state, infinite state. This is infinite strip. Let's call this omega, and this we call omega complement. So first question, omega, simply connected or not? It is simply connected. Well, you can use again the same straight line homotopy if you want, right? The answer is yes. Second question, omega complement, simply connected or not?
Also something. Well, no. No, because
So, what do you think?
Because the region interrupting everything.
Is it simply connected or not?
No, it's not.
Right, you said yes, then you said wait, no?
Yeah.
Yes, it is?
Oh wait, yeah, because we can see the whole thing as the Riemann sphere. So
Very good, right? So the answer is yes on the Riemann sphere. So
a lot of back and forth. Oh, we know.
yeah, I mean usually when you do complex analysis, you can think of the Riemann sphere, right? So you can just think about continuous at infinity, differentiable at infinity. So you can generally just do all of complex analysis on the Riemann sphere, right? So Paul is just another value.
I was just thinking, if you see that as R2, let's say, in that case it wouldn't be simply connected because the strip would be interrupting.
It would be interrupted. So answer on, which by the way confused the hell out of me. Confuse you, right? But I mean, I'm reading, let's say, alphas, and it is saying, well, it's something is simply connected if the object and its complement are both connected, right? On C infinity, yes, right? Because you can go pretty much from here all the way around. Yep.
So the only difference, whenever we mentioned that we're not looking at this in R2, we're looking at it in the Riemann sphere, the only thing we're doing is that we're assuming continuity at infinity. That's pretty much all.
I mean, I'm not sure what you continue.
We're assuming the one value.
Basically, there is a Riemann sphere, and it has a bunch of points, right? Like a globe, right? So what is the infinity point? It's just the North Pole, right? I mean, when you say continuity, is basically now what I imagine doing is that I can take a separate transparent layer of skin and cover the Riemann sphere, and then I start deforming it, right? So I can take this layer, and the skin is stretchable. So I can take the skin and I can, let's say, wrap around the Riemann sphere 2 times. What's the math? So if I took the skin, like here is the plane, and I pull the skin out, and I go like this, and wrap around twice around the Riemann sphere. What's the function that is doing it? You understand what I'm saying, right?
Not really.
No, okay. That's not also. Alright, so let's try to figure out what we're saying. So, it's not very important, but just since we're at the topic, right? So, this is the south pole, this is the north pole, right? And this is my Riemann sphere. So the way, one way to try to think of functions from the Riemann sphere onto the Riemann sphere is that we have this Riemann sphere and it has a flexible skin, right? And basically it has this, what I imagine that this plastic core, where I see all the points labeled, the plastic core, and it's inside, and on top of it I have a transparent stretchable skin. So the function applying to this Riemann sphere, Riemann surface just takes the skin and pulls it around it twice. So in other words, here's the skin, here is the point 1. Then if I just look at the point 1 on the xy plane, I see that as I'm stretching, it goes 1 times around and then 2 times around.
You're just modeling out for pi.
So each point, if I look at its horizontal motion, it's moving in a circle, and it's moving around twice. You see what I'm saying? So let's say here is the number 1. The number 1 was moved once, and then again. I was pulling the skin, so I dropped it out. So what's the function that is doing?
Identity?
No, okay, really. Z squared. Z squared, the double the angle. Yeah? Yeah? Well, it's just again, I understand.
Yeah,
But you understand what I'm saying, right? So what is the Z squared doing? It's mapping the Riemann sphere twice onto itself.
Because it's the magnitude, but it's still kind of same, but the angle's already.
Well, yeah, the angle is going to be just.
I was thinking about e to the 2iz, but it's to the argument of the angle, but that's still that's it.
Yeah. So okay, good. So no worries. Don't worry. I don't understand anything about the Riemann sphere. I'm just pretending that I do. So hopefully good, right? You're supposed to be giving evaluation, so just. Alright. So basically, what's important about simply connected region? Remark. On a simply connected region, we can mimic is double M to 1 M, no. Okay. We can mimic the construction of maybe A or of a primitive antiderivative for or of the holomorphic map. So what I'm trying to say is this. Also, we have a simply connected region. Right? So in this region, the function is holomorphic. So if in that region I select, in this region I can define, if I have a function f from omega to c, that is holomorphic, if f is holomorphic, then I can define the function capital F of z as follows. So I just fix some point z0. I fix some point z0 in this simply connected region, and f of z, capital F of z, will just be defined as the integral over the curve gamma from z0 to z of f of psi dxi. In other words, what I'll do is I'll locate any z, and just for any possible curve that I can find that connects z0 to z, that is piecewise smooth, rectifiable, that type of thing, right? I'm going to do this. Now this is well defined. You agree it's well defined? So 1, f is well defined on omega. What's a very easy value? F of z0 is what? Capital F of z0 is 0, right? It's because you take the constant path, it's 0, right? So f is well defined on omega because if alpha is another curve from z0 to z, then alpha is homotopic. To gamma, which implies that the integral over alpha from z0 to z is the same as the integral over gamma from z0 to z. So this is what we very, very rashly tried to prove at the end of last class. It's an important idea to understand. Again, if you haven't followed what we were talking about, just try to reach time. It's explained, I think, well enough, and it's really a proof that it's very important, but I hate kind of reproducing it. It's really just tedious. Right? But the consequence is really important. The consequence that I can create such functions. And if I can create such functions, then this is how you create an antiderivative. Right? So, and the second part, I'll just let it, you can verify it by yourself. The derivative f prime of z will be little f of z. And the reason for that is, again, right, what you can do is you can just take any curve to z and extend by a small straight line to z plus h. Right? And then you have f of z plus h minus f of z is just going to be the integral over the small segment. And because the function little f is continuous, it's like really integrating h times, it's like f of z times the length of the segment. That's really the essence that's happening. That's really what made the fundamental theorem of calculus work, you know, in Calc 1. It's really exactly the same idea. Makes sense, everybody, right? What you do is just extend it a little bit. That would be z plus h. And
I think we did the proof last time.
we did the proof several times. The same idea, pretty much, right? So, but you can just kind of fix the curve gamma and then adjoin to it a line segment, a very small line segment to z plus h. And then the difference of the integrals is the integral over this region. And over this region, because it's really tiny, it's approximately h times f of z. And if you divide that by h, you just get f of z. That's the essence of the idea. Good? So the ability to, so basically simply connected regions allow us to always find antiderivatives for stuff. So now we can talk about the logarithm. And one question actually that was on my qualifying exam was pretty much about the logarithm. And so I was very happy. So, complex logarithm. you have seen it defined before. So if we want to solve the equation, e to the power of w of z equal to z. Right? What must be this function? So then what you do is you take the absolute value of e to the wz, which is just simply because of properties of exponential maps. This is e to the real part of w, and that would be the absolute value of z. Right? And because this is now an equation that you know how to solve from Calc 1, you know that by taking logarithm, you know that the real part of w is equal to ln of absolute value of z. Right? Now, the other part is that we know that we can then write e to the w as absolute value of z times e to the I imaginary part of w. And that is supposed to equal to absolute value of z, e to the I argument of z. So this is just e to the I something. It just gives you the unit vector, right? This is just some unit vector in the direction of z, right? So the conclusion is that wz will then have to be defined as ln of absolute value of z plus I times argument of z. And this is the part that is not usually well defined, because the argument you can specify any addition by 2 pi or subtraction by 2 pi, right? So this part is the one that makes it difficult. So if you can go, if you have a region where you can go around the origin once, or then this will not be well defined. So that was we spoke about the argument principle and whatnot. So here is how we can try to consider how do you define. So this is not single valued. So on the other hand, so let's actually prove this theorem. The theorem is this. So suppose that we have omega simply connected region. With 1 being in omega. And very important is that 0 is not in omega. So we are saying if we take any simply connected region that contains 1 and avoids 0, then there is a branch of the logarithm and we can call this capital F of z equal to log at omega of z, so that the following properties hold. Property I, so F is holomorphic. In omega. Second property, if it's the logarithm, it means that if I take e and place f over e to the f of z is equal to z for all z belonging to omega, and third property, we can write that f of r is equal to ln of r wherever or whenever r is real and near the point 1. Okay? So, proof. So, okay, first question is, how are we going to use the simple connected property? How are we going to define this function f of z? Any ideas? How to define f of z?
We use branches, so we cut and then...
Well, we don't know the shape of it. We only know that it's simply connected, right? So what does it mean that we know that it's simply connected? It means that if I select any two paths in omega, I don't know the shape of omega, but I know that if I select two paths in omega that have the same endpoints, I can deform one path to the other. So that's the only thing I know about this relation. How, using this information, am I going to be able to create the logarithm? So also I know 0 is not there, very important, right? 1, by the way, it's only to make the logarithm remind you of your usual logarithm. If 1 is not there is not a problem. It's going to be still a logarithm, just not like the one you're used to. Okay? So what am I going to do? Ideas. How is logarithm defined in Calc 1? I mean, really.
That way?
Well, I mean, really there are different presentations of it. They're not rigorous, but a rigorous definition of the logarithm is what? It's the integral of 1 over x, right? 1 over x or 1 over z, right? So exactly this way we have to define. We know that 1 over z is going to be a function that is holomorphic over omega. How do we know that? That's where we need that 0 is not there. If 0 is there, boom, right? It's not holomorphic at 0. Well, that's very annoying. It's not holomorphic at 0, but if you look at it as a Riemann surface, then it is. Right? So, but because you can differentiate at infinity, okay? But so there's this, in terms of the complex plane, it's not holomorphic at 0. In terms of the Riemann sphere, it is. So you can, so that's rational math, right? So what we do is we're gonna say let f of z be equal to 1 over z, which implies that f from omega, and let's emphasize c, right, is holomorphic. Let capital F of z, in other words, if it's holomorphic, what we just remarked is if a function is holomorphic, you can construct an antiderivative over a simply connected region, right? Because we do that using integrals over curves. In Calc 1, why is every function have an antiderivative or a continuous function? Well, because R is simply connected. That's, you can just always define an integral, right? You can always deform one path to another, but it's not very noticeable. But that's really why in Calc 1 the statement is true, but in Calc 3, well, in complex analysis, not every holomorphic function has an antiderivative. So we can define f of z to be the integral. Now remind me, where do I want this function to be equal to 0? Logarithm at what value is equal to 0? 1, right? So therefore it's convenient for me to pick the, that's why I selected this one, right? I could have picked another logarithm defined from a different point, but let's actually define this to be the integral over any path that starts at 1 and ends at z of 1 Well, I mean, I already called it f of z, so I'll call it f of psi d psi. Right? Then, and I should mention of course, that this path has to be a subset of omega. Then, what's the derivative f prime of z? Yeah, f of z. Again, just make sure you understand the construction guys. Make sure that I brushed over it just a moment ago. Make sure that you can actually explain why that is the case. At least on an intuitive level. So this is f prime of z equal to 1 over z. Alright, so that's fine, but how do we know it's the logarithm, right? Now, so this takes care of number of condition I. So I created I didn't explain its logarithm, but I did explain that the function is holomorphic, since well, I take its derivative, it's 1 over z. Right? This takes care of 1. Now, now I want to prove number 2. So we would say that e to the f of z is equal to z if and only if 1 is equal to z times e to the minus f of z. Right? I don't know that this is equal to z just yet. I suspect. Because the derivative is 1 over z, that's the derivative of the logarithm, but I want to show that e raised to that power will give me z. So that's what I do. So I'm going to show this. Now, what's the derivative? So if I take ddz of z e to the minus f of z, what do I get? I hope to get 0, obviously, right? So what do I get? I get e to the minus f of z, and then minus z times 1 over z e to the minus f of z, where I just apply the chain. Right? And what do I get? I get 0. That's already a good sign, right? So I get 0. Now I need to determine, so the implication is that it's 0 over derision. The implication is that z e to the minus f of z is equal to the constant, c. Now how can I determine this constant? What value am I going to plug? 1, right? So we plug in 1. So we have now that 1 times e to the minus f of 1 is equal to the constant. And that implies that 1 times e, what's f of 1?
Wait, capital F of 1 or little?
Yeah, capital F of 1, yes. This is the integral from 1 to z. 0, very good. So this is e to the minus 0, and what I get is 1. So the implication is that c is equal to 1. Wonderful, I finished that part of the proof. Right, so again, just so you see a picture here. The picture is that here is the region omega, it's simply connected. Here is the point 1, and if this is the point z, what I do is I just reach the point z by some path gamma, and I integrate, right? So if I integrate from 1 to 1, if I select z equal to 1, then there is no path to integrate over, there is 0. So c is equal to 1. Very nice. So it is already, now this makes it a logarithm, you agree? E to the power of f of z is z, that makes it a logarithm. Now finally, how do I observe condition number 3? It's trivial. Condition number 3, that's actually, now how do I observe condition number 3? That f of r is equal to ln of r. Well, I can select a path I mean, if I look at my region, here is 1, and 1 is contained in some open ball because I have an open set. So if I have 1, I also have some runway. I have some runway that is only on the x-axis, right? So something like this. Is contained in my region omega. Right? So if it's contained in the region omega, what I can do is I can select R to be here, select the value of R to be here, and select this path. Select the x-axis, right? So then what I have is that f of R is simply the integral from 1 to R of the function 1 over z dz, but dz is on the x-axis, right? So this is simply the integral from 1 to R 1 over x dx, which is ln of R. Okay, and the reason that we say where R is real and near 1, the reason the word near 1 is because I don't know how much of this runway I will have. I might have a very tiny runway. Maybe this region omega does not intersect much with the real axis. Right? It might just intersect for a moment and then afterwards it's not there. Just barely touches it. But because it contains 1, there is at least a ball. And there is at least some interval segment where it is touching the x-axis, where it's containing the x-axis. So this is now your logarithm, and over simply connected regions you always have a logarithm. Alright? So let's just write one example. We can actually see how the standard, the principal branch of the logarithm can be derived from this technique. If you have the split plane, so if you have omega is equal to c minus infinity to 0, so it's the split plane. So this is simply connected. We know that 1 belongs to this region, and we know that 0 doesn't belong to this region, right? So there is a logarithm. Now how can I define the logarithm? I can, for picking up a value z, what I can do is I can move down to the absolute value of z. So this is just the absolute value of z, which is contained in this region. And then this arc. So what I can have is, this is the arc. So what I can define is, I can say that capital F of z is going to be equal to the integral from 1 to absolute value of z of 1 over psi dxi, where this I mean is on the real axis, right? So this is where this is taken. You see, I can always change this I can change the path to be anywhere I want in this region. I can force it, I can deform it partially to be on this axis, right? So any path starting at 1 and ending at z can be deformed into a path that consists of two segments. One segment is this, and the other segment is the arc. Right? plus we can parameterize this arc. This arc is parameterized to, this is argument z, so this arc is parameterized as the integral from 0 to the argument of z of 1 over absolute value of v e I theta times I e I theta d theta. Actually, the absolute value is so I get ln absolute value of z plus, that's it. Yeah, I forgot that the absolute value of z will be here as well. So they cancel. So you see this, I just didn't want to write it another way, parameterize it, right? So it's going to be ln of z plus what's the integral, plus the integral from 0 to arc z of I d theta. So what I end up having is ln absolute value of z plus I arc z. In this case, arc z, so that it has a precise meaning, it's going to be a number between minus pi and pi. So this is called the principal branch of the logarithm. Okay, make sense? So here is a generalization of the theorem. So they asked, this is a question actually was asked on my qualifying exam, one of them. So theorem. If f is nowhere vanishing, holomorphic function in a simply connected region gamma, then there exists holomorphic G from omega to C such that f of z, the region, the function that we selected, is e to the power of g of z. The function gz is denoted by log f of z. So you see what I'm saying? So any nowhere vanishing, any function that never takes the value 0 on omega has a logarithm, where omega is a simply connected domain. Let's try to prove it. proof. So we have a simply connected domain. This G, I need to construct it. This G has to be the logarithm of f. How am I going to define it? Think about it. All I can do is a simply connected region. It has to be in terms of integration. How am I going to define it? Sorry?
Monobrief of Z.
Something with Z? Integral? Right, think back to Calc 2 or something, right? When you have an integral of something and you get logarithm. That's really what's going to happen, right? So you have an integral of some expression and you get logarithm. So for example, you integrated something and you got log of x squared plus 1. What was the function that you integrated?
1 over 2x over x squared plus 1.
Exactly. You integrated 2x over x squared plus 1. That's what you integrated to get logarithm of x squared plus 1. Similar idea is working here. It's just Calc 2. What am I going to integrate? I need the logarithm. I need the answer is to my question is I need to find g. My answer is log of g of z. So log of f of z. What am I going to integrate?
F prime over f.
Yeah, f prime over f. Brilliant. You see that, guys, right? So what we're going to do is we're going to fix some point z0 belonging to omega. Define well, let's not right away say this is g. What should I say this? Let's define k of z for now, because I'm not sure. I think maybe I'll adjust it to make it more like because it will be pretty much this with plus a constant maybe. So define k of z to be the integral over any curve gamma from z0 to z of f prime psi divided by f of psi. That's where I needed it to be nowhere vanishing, right? Because if it's vanishing, it's acting like 1 over z. So f cannot vanish. If it's vanishing, then this is not meaningful. Make sense? So we have this. So then I'm going to now show that what I just wrote is the logarithm. So how am I going to do that? If I want to show that k is a logarithm, what am I going to do?
Take the exponential.
Take the exponential of it, exactly, right? So the next step is take the exponential. We show that k of z is some kind of log or logarithm. No, it's pretty easy. If you see where it's coming from, it's very easy. Just like really integrating a Calc 1 or 2 problem. So what we do is, by the way, how much time do we have? 15 minutes. Good. Right. Good enough. So we're integrating it. So what we're going to do is we're going to consider what is e to the power of k of z. E to the power of k of z. Now the question is, what do I want it to be? Want. So it's not. I don't yet know that, but I want this to be what? If I raise e to this, so what is this integral? In principle, forgetting about all those technicalities, this integral is log of f of z.
Oh.
Yeah, you see, not z. So I want it to be log of, so I want this to be. Exactly, right? So I want it to be f of z. And it's not possibly, it's not going to be exactly that, but it's going to be a constant times or something. So I'm going to upgrade it in a moment, right? So this would be f of z. So my first step in this proof is I'm going to write f of z times I'm going to consider f of z, or the derivative of f of z times e to the minus k z. See, it's a generalization of what we just did before. And basically, I'm hoping that f of z times e to the minus kz ends up to be the constant 1. Then I have shown that this is indeed true. But the first thing I want to show is that the derivative is a constant, in which case this is very similar. It's almost it's 1 or it's all. So what I do is I take the derivative, and what I get, well, I get f prime of z times e to the minus kz. And then what do I get? What's the derivative of kz? So then I get
F prime z.
Yeah. There's going to be a negative, so it's going to be minus f of z, f prime of z divided by f of z times e to the minus kz. And as you can see, the answer is 0. Wonderful. So first part is 0. So the implication is that f of z times e to the minus kz is equal to a constant. I need to know something about this constant. I really want this constant to be 1. How do I find what this constant is? What do I plug? Look at this definition. I pick a point z0. What do I plug? Z0. That's the only thing I know. I have no idea how this curve, what is it doing, right? I pretend that I know this integral, but I really don't know. Right? I just really just integrate it. It's very easy, right? Yeah. So what you do is you take f of z0, and here we have e to the minus k of z0. This is equal to f of z0, right? It's equal to f of z0 times 1. And that's equal to my constant. So am I happy with this constant? Yeah. Am I happy with this constant?
Wait, where do you get the 1 from?
Because this is a k of z0 is 0, and e to that 0, or maybe I'll do it slower. So this is e to the 0, which is f of z0 times 1, which is that constant that I claim this thing is, right? So am I happy with this constant? But my constant is, in other words, what I get is that, what I've just established is that e to the power of kz is equal to f of z0 times f of z. That's almost what I want, right? Because f of z0 might not be equal to 1. Might not be 1. So what do I do? Now this is just a constant, very easy. So the way you define g, so from there what you do is you define g of z to be equal to k of k of z so k of z, what is it, plus or minus the logarithm? Yeah, I think, yeah, plus any logarithm. That means just find any number that to the power of e will give you this stuff, right? It's just adding a number plus log of f of z0, which you know is not equal to 0, so that's okay. So by this log I mean just any value that solves the equation e to the w equal to f of z0, which is just a particular number. Okay. So what happens under this condition? Then you have that e to the power of g0 and gz is equal to e to the power of kz times e to the power of log f of z0, and what that ends up being is, it ends up being f of z0, and e to the kz, we just said it's equal to, yeah, so I guess I need minus, right? Minus log, and then it would be 1 over f of, so that e to the kz will end up being f of z0, f of z, that's e to the kz, sorry, times 1 over f of z0, and I end up having f of z, yeah, that works. So minus, okay? So that's that. Okay, so basically I just modified this function k by the appropriate constant so that it now is just the logarithm of that. Okay? Good.
Professor, shouldn't
Yeah.
that be 1 over f of z naught instead of f of z naught?
Well, that's the minus here.
I mean, but you said e to the k of z equals f of z naught times f of z.
Yes, e to the kz
Yeah.
is equal to that based on our calculations, right? So then...
Why is that?
Huh?
Why is that?
Why is that?
Yeah.
That we found the constant to be f of z0. So we found that f of z times e to the minus kz is equal to a constant because the derivative is 0.
Okay.
Derivative of this expression is 0, which means that this function is constant. Now you ask, what is that constant? The only way to figure out this constant is remembering what is k. K is this function. I know that if I select z equal to z0, k is 0. So if I pick and I plug here z0, I get f of